Okay, so this is the first video in a series on problems for 1073, Algebra for Scientists and Engineers at UTSA. And basically, this is a PDF that's available on Blackboard for Module 0.1, Video Lecture Class Examples. And I'm basically going to go through and work these examples out, and they might all fit on one page. We'll see how it goes. And yeah, I'll just work these problems out. And I might take some time, like scroll down, go find a blank page, and talk about the concepts a little bit. Or I might just go, "Here's how you do it." We'll take it as it goes. So, first example for the following exercises: perform the given operations. So, when we look at an expression like this, it might be something that you're really familiar with. It might be something that you haven't done in a while by hand. If you've been using a calculator in high school, in your math classes and your science classes, then yeah, you might look at it and go, "Yep, those are symbols." So there's a couple ways to approach this, and one is to think about order of operations, PEMDAS, right? And I have some problems with PEMDAS because it can be misleading, it can be misused, and I think one of those are practical problems with it. One of the main problems I have with it is that it presents things as a rigid structure, like you have to follow these rules, and it's really not how math works. There are things that are reflective of meaningful arithmetic and things that are not. And by experience, you learn which things are useful and which ones are not. So PEMDAS is a shortcut, a way of saying, well, here's basically the concept, but you have to keep in mind that it is overly restrictive. It's going to tell you to do things that you don't necessarily have to do sometimes. So this stands for parentheses, exponents, multiplication, division, addition, subtraction. There are 6 things. Part of the problem is there are actually 4 things, not 6, because multiplication and division are really 2 sides of the same coin. They're really division is just backwards multiplication, right? Like when you learn division in first grade or kindergarten or whatever, you do multiplication first, and then you learn division in terms of thinking through multiplication backwards. Same with addition, subtraction. Subtraction is just backwards addition. When first grade, kindergarten, whichever it is, I guess kindergarten, I suppose, I don't remember now. Um, when you learn addition, through counting, right? 3 plus 4 is 7 because you have 3 apples and 4 apples, you count them, you have 7, right? And then when you learn subtraction, you work backwards through addition, right? 5 minus 2 is 3 because 2 plus 3 is 5. So really, there's 4 things, and I would think that PIMA would make more sense, like if we got rid of that with the understanding that division, subtraction are special forms of multiplication and division, multiplication and addition, respectively. Anyway, you're all familiar with PEMDAS, almost certainly. So we're going to basically use that. When we're doing arithmetic like this by hand, we move left to right following PEMDAS. So we resolve all parentheses first. Parentheses comes first. You deal with parentheses first, right? So we've got 40 divided by 20 because of the parentheses. I got to deal with this first, right? 4 times 5 is 20 plus 24 divided by 6. Now, obviously, I could have done some of this earlier on by following PEMDAS to the letter. It's overly restrictive, but I'm going to follow it to the letter. Next, I go with exponents. Well, there aren't any, so ignore that. Next is multiplication, but really, it's multiplication and division left to right. So both divisions go at the same time. So 40 divided by 20 and 24 divided by 6. So I'm going to have 2 plus 4, and then last I have addition subtraction, so I get 6, right? So PEMDAS is useful and effective, but be aware that it is restrictive in that it's a recipe. It's step by step. Do this. And so it's easy to use, but it is more restrictive than it really has to be. So I will try to avoid saying that 1,000 times in this video. So moving along, just looking at this, you could probably tell what happens first, right? PEMDAS. I'm not going to write it every time. So parentheses, well, there aren't any. Exponents, there aren't any. In fact, can we zoom in? Yeah, let's zoom in a little bit more. Exponents, there aren't any. So multiplication, so this product goes first. So I'm going to have 3 minus 48 plus 18, okay? Now, there's no division, so we have the AS step, addition, subtraction. So, you know what, I will write again, because this is important. This is part of where people can make errors Potentially, if it's misunderstood, if I could write it in A, there we go. It would be a mistake to go, oh, 48 plus 18. That's going to be, what is that, 66, right? That would be incorrect because this 48 is not positive, it's negative 48. So if you wanted to, you could resolve this first, right? But that is not what PEMDAS is typically taken to mean. You just do it left to right, addition and subtraction at the same time. So 3 minus 48, that is negative 45, plus 18. Add those together. What is that? Negative 27? Negative 27. Now, you can do things in a different order. It's just I'm going to show how to follow PEMDAS. But there are options. There are other ways to do this. So next thing, PEMDAS. So parentheses first. So whatever's in parentheses, resolve that first. So 9 squared. 9 squared divided by 3. Okay. So next, exponents. So we square that. 81 divided by 3. Right? Now I can divide it because I have no multiplication. I'll do division. So I get 27 and we're done. There's no addition. There's no subtraction. Now there was addition, but it had to happen first because it was in parentheses. Okay. So now we're getting to things a little more complicated. We have layers of parentheses. We have brackets in parentheses. So again, PEMDAS. Parentheses first. And we have two, let me change settings here a little bit. I've got 2 layers of parentheses. I got brackets and parentheses. You always handle the innermost ones first. So step 1, innermost set of parentheses. So I'm going to replace that with a 4. And I will write the whole thing every time. I won't cross it out and write a 4. I'll write the whole thing. In part because it's just easier to follow in a video. And also, when you're doing this on paper, I know it can be tempting to just go at 4, at 16. But then when someone goes to read your work and grade it, especially, in this class and later classes, it's gonna be hard for them to follow what you're doing if all of the old steps are completely scratched out. They can't even read what you wrote half the time or 80% of the time. So it's tedious, I know, but it's just good practice to write the whole thing again. It's being thorough, right? So now, I'm still on P, parentheses. But within the brackets, within these parentheses, there are several things. So I have to restart my approach to PEMDAS. Well, parentheses, but within those parentheses, there's multiple things. So within the parentheses, I go to E, exponents. So I have to handle this first. So this is going to be negative 2 times bracket 16 divided by 16, right? 4 squared is 16. Now I can go ahead and continue in the parentheses. I have no multiplication, so I'll handle the division. 16 divided by 16, which will be 1 squared. And now, inside the parentheses is pretty much resolved, right? And I'm running out of room, so let's go up here and start a new column. So now I can square that 1, negative 2 times 1. And you might go, why are you doing it in 2 steps? Just say this is negative 2. Well, yes, but I'm showing PEMDAS 1 step at a time. And then multiplication, negative 2. Okay, so following PEMDAS. You can do things out of order. I'm doing air quotes. You can't see I'm doing air quotes. You can do things out of order, but I'm just showing PEMDAS. So what's next? Oh, and by the way, if I'm going too fast, you can always pause and think about what I'm saying. You can always, since this will be on YouTube, at least that's the plan, you can always slow it down to 75% speed. Click the little gear icon and change the speed if you want, or speed it up. Slow it down, speed it up. That's up to you. So now we're going to simplify these expressions. Now I look at this one. I think I see something I can do with that. And there's a number of approaches. So I'm going to do what's called a prime factorization. I'm going to make a factor tree. I wish I had more space. I'm going to have to adjust this for the next video. I'm going to make a factor tree. And I think that is the best way to get started for most people. You might be able to look at that. This number's kind of big. But if the number was smaller, like the square root of 100, you might go, oh, that's 10. I know that. Right? Square root of 144, you might know, oh, well, that's 12. There might be a few that you just remember. This one, maybe you don't. Probably not, I guess. Most people probably don't. So I'm going to think, well, I noticed that this appears to be even, right? The last digit is even, so the whole thing is even. So I'm going to factor this as 2 times, well, what's half of 324? Well, half of 32 is 16, half of 4 is 2. Oh, it's still even. Well, you know what? Let me divide by 2 again. And that's going to be 81. Oh, 81, that's 9 times 9. Oh, wait a minute. I'm doing a square root, right? And I have a pair of 2s and I have a pair of 9s. That means I'm done. I don't need a prime factorization. 9 is not a prime number. I don't really need that. I'm looking for pairs. Pairs of numbers. They don't have to be prime. So I'm going to rewrite this as the square root of 2 squared times 9 squared, okay? Everything that's at the end of a branch, or I guess a root, in my prime factorization tree, I need to represent here, okay? And these are squared, of course, because there's 2 copies of 2 and there's 2 copies of 9, right? Maybe that's obvious to you, maybe not. I'm just trying to be thorough in the explanation. There's a couple ways to talk about what's going to happen next. And I'll just be as straightforward as possible. When you have a squared number inside of a square root, that number can come outside and it loses the root. Like this exponent gets used up. It's like a key to get outside the door, right? It has to use the exponent to get outside. It's used up. So that 2 comes out. As well, this 9 comes out because it also has a square. So I have 2 times 9 and left over inside. And this is something we might have to talk about more. I have 2 times 9. And when you remove those elements from inside, those factors, there's a 1 left over. There's always a 1 left over. And of course, the square root of 1 is 1, right? Because this means, what do you multiply by itself to get 1? Well, that would be 1. 1 times 1 is 1. So 1 is the result. So I just get 18. 2 times 9 times 1, which is 18. Now, maybe for some of you, you might look at this and just recognize, oh, 18. If in middle school, high school, they made you memorize these things, then you would know that. I think when I was in middle school, they made us memorize up to 20 squared, I think. So some of them I remember, right? And if you do, that's great. And if not, if you don't remember, well, this is the method to do it. You do a factorization tree. You break the number down into pieces. 2 times 2 times 2 times 9 times 9 is 324. And when you break this down in pieces, you can then move those pieces in pairs outside of the root and get your simplified number. Okay. So what's next? Well, now we have to do this with a variable involved. Okay. And I noticed there's no other directions. It was just, I believe it said simplify. Yeah, simplify, right? And we're not told what p is. I think we're meant to assume that p is some real number. It's a whole number, a fraction, a square root of something. Maybe it's pi, something like a real number. You might recall from high school, maybe imaginary numbers. There's no imaginary numbers at this point in the class. We'll see those later in the class, but not right now. So I noticed that 36, this is 6 squared. Okay. I'm going to do this one a little bit different from this one, I think. I think it'll help. So I'm going to rewrite this because, of course, struggling with the interface here. Of course, 36 is 6 squared. So I'm going to write this in the following way. I'm going to write this as the square root of 6 squared. Well, you know what? Let's do it in 2 steps. Let's say 36 times the square root of p to the 4th power. Okay. So when you have factors in a square root or a cube root or a 4th root or whatever, you can separate the factors and they each get their own root. Okay. Now, of course, the square root of 36, well, that being 6 squared, was going to be 6. Over here, where I have p to the 4th, I notice that when you have something to the 4th power, this is the same as having the square squared. So I'm going to rewrite this as the square root in parentheses p squared squared. And just like I said earlier, anything that is squared can come out front, okay, and lose its squaredness. It loses that exponent. So for the p, I've got p squared squared. This exponent there is going to remain. This one will get used up. It's the outermost one. The order actually doesn't matter, but we can think of it as being the outermost one for now. Maybe that will come up again later. We can talk more about that. So, almost out of rooms. Start a new column here. So this is going to be a 6 times 1, I guess, but we don't need to write it. Or you can think, this is slightly problematic. We'll talk about this at some point. You can think of this as canceling, but that's not quite right. There's a little bit more to it than that. I'd rather think of it as using up the exponent to get outside of the root. And for a number, you just put the number outside. In fact, after we talked about this one, I am going to go, I'm going to talk about an exception a little bit after this. So here, again, we use up this exponent to get outside. We get p squared. Okay, so the square root of 36p to the fourth is 6p squared. So I want to talk about the exception to that. Well, not the exception. There are two, I suppose. If I had the square root of x squared, right? Then this is not x. Okay, it's a little bit more complicated than that. Here's why. If I take like the number 5, right, and I square it, of course I get 25, right? And if I take the number negative 5 and I square it, of course I get 25, right? Negative times a negative is a positive. Now, if I had been square rooting that all along, I would get 5 as a result in the first case. If I had been square rooting this all along, I would get 5 again as a result in the second case. So in the first case, the number you started with is the number that you get as a result. Squaring and then square rooting in succession like that, the result is whatever you started with. There's no change. If something, we'll say that in a second. See if you can tell what the difference is. When I start with negative 5, I still end up with 5. These two are the same at the end. So if I tell you I have a number and I square root, I have a number, I'm thinking of it, and I squared it, and then I applied the square root, and I got 5 as a result, how do you know which one I started with? Right? Like if I pick one randomly, I suppose, and I square it mentally, okay, I got a number, and I square root it, and I get 9. Well, did I start with 9 or negative 9? How do you know? And the answer is you don't. It's you guess, and it's 50-50 chance, I suppose. But you don't know. So the square root of the square is not merely the thing you started with. Okay, what it is, and I don't know if I'm going to get a little bit ahead of myself. I imagine this is something you've seen in high school, but perhaps you've forgotten about it. Who knows? In an in-person classroom, I just ask guys, like by show of hands, who remembers this? But of course, in a video, I can't do that. So, absolute value of x. If there's a negative at the beginning, it gets used up and thrown away, because when you square a negative, you get a positive, right? As we talked about a moment ago. So that's one exception to canceling roots. That's why I said I don't like to think about it as this root canceling, because it's not, as the root canceling, it's not quite right. But it's one way to think about it, but really, you have to be careful. When you have an even root of an even exponent, well, basically, when you have an even root of an exponent that's a multiple of 2 but not a multiple of 4, then you have to worry about absolute value. This one we didn't, because p squared is always positive anyway. So I could write absolute value. That's fine. It's redundant, because p squared, when you square a number, the result is always positive. It's just redundant to say that. I don't need to say it for that one. Anyway, from time to time, I'll give an aside, some extra information. But moving along from that one, C. Now, these are two that I happen to remember. If you don't, what you can start doing, either on paper or if you're using a calculator, you could just, obviously you could type into a calculator, but you could think, okay, well, what's 10 squared? What's 11 squared? What's 12 squared? You might think, okay, what's 15 squared? I might have to write this out and do long form multiplication, right? And it's a bit of a pain, but you get the result, right? 225 is the square of 15. So I look at those two, and I remember that the square root of 289 is 17. And I remember that the square root of 361 is 19, right? So I get, was that 34? This is not, it is definitely not, is that a sad face? I want a sad face. Is that a sad face? I don't know. This is definitely not the square root of, is that 450? 650. It's definitely not. That is not how roots work. They don't combine that way, right? 34 squared, well, the square root of 650, if you throw it in a calculator, it's not going to be 34, I can tell you that much. 650, I sure hope I did that right. It's about 25.5, right? It's 625 is 25 squared. So yeah, that seems right. These are clearly not the same thing. So when you have two roots like that, do not, and they're being added, between the roots, a root plus another root, do not add the numbers inside. These are each called the radicand of the respective term. Running out of room here. Okay, what's next? Are we done? No, we got one more, and then I think one more after that. Yeah, okay. So with this one, this is definitely not. This is definitely not. Was that? Would that be 128 if you just subtracted them? It's definitely wrong. Don't do that. That's very wrong. They do not combine that way. This is 18 minus 14, I think, and I get 4 that way. Okay. Next, the cube root. Okay, so I noticed that 8 is 2 cubed, and I noticed that 125 is 5 cubed. There's actually a couple ways to work this one out. So I'm gonna go the route I've just pointed out. Okay, so when you have an exponent that matches the root, kind of like up here, we said that in fact, let's go to this one. We said the 2 and the 9 can come outside. That's because there's an implied, not written, but implied 2. The index of the root is 2. And since those two guys match, the 2 can come outside. And since, hit undo 120 times. Since these two guys match, the 9 can come outside, right? The exponent and the index of the root match. Yeah. Because of that, in this case, the 3's match. The 5 can come outside. As well, the 2 can come outside. Like I said, there's more than one way to do this, and I'm just going to go forward with this method. So the 5 comes out, and the 2 comes out, and the 2 stays in the denominator. It's still in a fraction. And then I have the cube root of -1. And that part might seem like it's a little bit hard to deal with. And there's more than one way to deal with this, actually, but I had to pick one. The cube root, rather, of -1 is, well, -1, because so if you say cube root of -1 equals, I don't know, I'd say s for something, right? That means that -1 equals that something cubed. So what do you cube? What do you multiply with itself 3 times, 3 copies to get -1? Well, -1 times -1 times -1, that is -1, right? So this is -1. So I guess I'll have 5/2 times -1. This equals -5/2. I believe that's the last one. Yeah. So anyway, those are the examples for Module 0.1. Maybe that was really straightforward. Perhaps not. If it wasn't, then please use the tutoring lab, ask for help. If I'm your instructor, email me. If this is an older video, email your instructor.